We're going to start today by differentiating the tangent function. So far, I've been using the ddx notation in front of functions like this to emphasize take the derivative with respect to x. But like you see on the board, you also should be able to use prime notation. It's a little quicker to write. It is a little inferior, you might say, because you're not specifying what the variable is. And there are situations where you might have more than one variable, like in multivariable calculus. By the way, we will actually talk a little bit about multivariable calculus in coming weeks in this class at a level that's understandable. It's not a full class by any means. To find the derivative of tangent, which is a derivative you should know and have memorized for the gateway exam, write tangent of x as sine of x divided by cosine of x. In other words, write it as a quotient. Why is that true? It's the definition of what tangent is. Yes, there's SOHCAHTOA for right triangles, but sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. TOA, tangent, is opposite over adjacent. However, if you take opposite over hypotenuse, all divided by adjacent over hypotenuse, the hypotenuse cancels. And you get opposite over adjacent. Tangent is sine divided by cosine, whether you're talking about right triangles or unit circle definition. As a quotient, we need the quotient rule. Don't hum or talk out loud during the test, but in your mind say, I highly recommend doing it the way I do. Low d high minus high d low over the square of what's below. Remember to start with low. Always start low. You could always start low. Low d high minus high d low over the square of what's below. Okay. Always start low. Low is the cosine. D high means the derivative of the high function, which is sine. If you're showing your steps like I'm doing right now, include a prime there. Otherwise, it's wrong because I haven't taken the derivative of that yet. Low d high, d means derivative, minus high d low over the square of what's below. And I almost made a mistake there because I said square as I was trying to write the prime and I wrote a 2 at first. Over the square of what's below. Not done. Take all derivatives. If this were the gateway and you were showing your work like this, you would not be done. The derivative of sine is cosine, so we get cosine of x times cosine of x. The derivative of cosine of x is negative sine x, and if you're writing it with a minus sign like I just did, you need to use, well, at least a dot, but I use parentheses for emphasis. You might say, Dr. Kinney, you overuse parentheses. Well, better to overuse them than to underuse them. They do, if you did not put a dot there and did not put parentheses, then it's like sine of x minus sine of x, and that's not what we're doing. It's sine of x times negative sine of x. This can be simplified. This is technically correct. That would be good enough for the gateway, but it's good to simplify it. Cos x times cos x is cos x quantity squared, just like in the bottom, but don't cancel because we're going to do something else. I hope you remember you can write that like that. And in fact, you can write the bottom like that too. That is notation. Remember, this notation means take the cosine of x first, then square it. It really means this. This is actually better notation to emphasize to take the cosine of x first and then square it. But that's more traditional because people are lazy. Including mathematicians are lazy. It's just a little quicker to write. But it really means this. Two negative signs make a plus sign. This negative can be, in a sense, factored out because it's really like a -1 multiplied times these things. And the -1 by the the commutative property of multiplication can be brought over here in front of that negative sign, and then the negative signs can cancel out. And you get sine squared. But wait a minute. Oh, there's our favorite thing to see in trigonometry. Cos squared x plus sine squared x. It equals 1. Remember, that's an identity. It's always true. Not an equation to solve for x. That was a true-false question on the exam. Cos squared x plus sine squared x always equals 1, no matter what x is. As long as these two inputs are the same input as they are here, the same letter, the result is 1, an identity. So one simple form of the answer is 1 over cos squared x. Since 1 equals 1 squared, and since the ratio of two squares is the same as the square of their ratio, and since 1 over cosine of x is also called secant of x, another form of this answer is secant squared x. And that's, you might say, the simplest form of the answer. But both of these are still relatively simple. They are equal to each other by the definition of secant. As long as you're not dividing by 0. Where might we be dividing by 0? We'd be dividing by 0 when cosine of x is 0, which is occurring where? Think about the unit circle definition. Cosine is the first coordinate. Remember the bug going around the unit circle? Cosine is the first coordinate. That's 0 when you're on the vertical axis. Angle 90 degrees, in other words, pi over 2 radians. Also 3 pi over 2 radians, 5 pi over 2 radians, 7 pi over 2, 9 pi over 2, 11 pi over 2, 13 pi over 2, blah, 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 blah. Negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, negative 7 pi over 2. Any odd multiple of pi over 2 is a place where this is undefined. It's also a place where tangent is undefined because you're dividing by cosine there. You might wonder, what do the graphs of these look like? Real quick sketch. Graph of tangent. Well, the basic piece in the middle here looks like this, with vertical asymptotes at pi over 2 and negative pi over 2. And then it's periodic with period pi, it turns out, actually, not 2 pi. Maybe you never knew that. Tangent graph has period pi. You might see if you can figure out why, if that interests you. Other vertical asymptotes occur at other odd multiples of pi over 2. And this graph goes forever and ever in both directions with that pattern. That is y equals tangent of x here in black. Let's make the derivative secant of x in a different color, secant squared, which is 1 over cos squared. It might be helpful to also graph cos squared x in here. Is that helpful? Yeah, maybe just to see the relationship. So I'm about to draw cos squared x. It's not the derivative. 1 over cos squared x is the derivative. Cos squared x is always positive or 0 at certain spots. Oh, what does it look like? I think it looks about like this. It kind of looks like a cosine wave, actually, except shifted upward. It's not exactly a true cosine wave shifted upward with the same period, at least. It's got period pi instead of 2 pi. That's pi right there. See, I believe it's actually cosine of, it equals cosine of 2x, 1/2 cosine of 2x plus 1, something like that, or plus 1/2. Actually, yeah, I think it does. Yeah, that's an identity. I knew that. That graph is cos squared x, and there is a trig identity that says that's 1/2 plus 1/2 cos 2x. And that's actually a useful identity to know in calculus 2, that these are equal, because in calculus 2, you have to do lots of integration integrals. And to integrate cos squared x, it's better to write it like that. It's a lot easier to integrate this directly than this directly. Of course, once you do this, then you've really done that, because these are equal for all x. Anyway, this is not the derivative, because the derivative is 1 over cos squared x secant squared x. What we need to do this graph to graph 1 over cos squared x is effectively, we need to imagine taking all these outputs and taking 1 over them. Now, if the output is 1, like it is right there, the 1 over 1 is 1. If the output goes to 0, 1 over something going to 0 goes to infinity. And these are all positive outputs, so the output's got to be positive. The graph's got to look something like this, and in fact have a vertical asymptote at negative pi over 2 and positive pi over 2. And it repeats. This picture here, the green graph, is a periodic function that is the graph of y equals secant squared x, 1 over cos squared x. And it is the derivative of the black graph. At every value of x where the black graph, the tangent function, is defined, the green graph, secant squared, gives you the slope of the black graph. You can see the slope is minimized at inflection points where the graph changes from concave down to concave up. That's where the slope of the black graph is 1. Otherwise, the slope is bigger than 1. And yes, it approaches infinity, as for example, x approaches pi over 2 from the left. The slope of this black graph approaches infinity, just like the value of the green graph approaches infinity. And over here, as x approaches negative pi over 2 from the right, the slope is going down to, is going up to plus infinity, just like this green graph is going up to plus infinity. These pieces of the green graph look like they might be parabolas. They're not. They just kind of look that way. They have vertical asymptotes. Parabolas don't have vertical asymptotes. Okay, so there's a rough showing of what's going on graphically. Second problem was to take the derivative of x squared times tangent of 3x. If we were going to do this from scratch, we'd want to write tangent of 3x as sine of 3x divided by cosine of 3x, right? Since tangent of x is sine of x divided by cosine of x, tangent of 3x is sine of 3x divided by cosine of 3x. Maybe multiply x squared on the top, use the quotient rule again. And also we need, in taking the derivative of tangent of 3x, we need the chain rule because we have an inside function there. That's not just an x, it's a 3x. Remember what the chain rule says. I'll write it down again right now. I'll use ddx notation to differentiate. Let me use different letters than an F and a G here. Let me use a G and an H since I have an F there. To differentiate the composition of two functions. G compose h of x is what we say. Sometimes it's written G circle h of x. Maybe you had a teacher who wrote that. Maybe you didn't in your past. The circle means function composition. It's kind of meant to be similar to the idea of an addition sign or a multiplication sign. But it means this. It means apply h first, then apply g. Work from right to left, inside to outside. Question? You could call it the composition rule, but yes, these functions are in a chain, and that's why they call it the chain rule. If you ever had a teacher who said, hey, you can pretend functions are machines, we can imagine two machines, one for the function h and one for the function g, that are chained together here. Imagine chaining these together. Okay, this is supposed to be a chain there. To get one new function, one new machine, G compose H. That takes a number X, you plug it into the H machine, you get a number H of X out. Oh, I should have had a little bit more space there. That's H of X. Hard to see, I'm sorry. That's an H of X there. Then take that number, plug it into the G machine, and get G of H of X. So yes, these functions are kind of chained together. It could be more than two of them in a big long chain. And the chain rule can be applied to more than two of them, though we mostly avoid that. At least when we write down its abstract formula. And what the chain rule says is take the derivative of the outside function, the g function in this case, the second function in the composition, the outer one, plug in the inside one, then multiply times the derivative of the inside one. That's what the chain rule says. It's not clear how to apply it yet. Let's start doing so. I also need the product rule. There's my left function. There's my right function. Lefty right plus righty left. Right? Correct? Lefty right plus righty left. Left, x squared, d right. Oh, there's where I need the chain rule. So I'm going to just write this as tangent of 3x prime first. Plus right, tangent of 3x. D left, the derivative of x squared is 2x. I'm not done because I haven't taken the derivative of tangent of 3x yet. Use the fact that we just derived 5 minutes ago. The derivative of tangent of x is secant squared x. But also use the chain rule. This is a composition. 3x is the inside function. Tangent is the outside function. In this formula, 3x is like the h of x. Tangent of x is like the g of x. The chain rule says, take the derivative of the g, the outside function. The derivative of tangent is secant squared. But wait, don't plug x into that, plug h of x into that. Don't write x here, write 3x. That's probably the most common mistake people make. Plug in the h function into g prime. Then multiply that by h prime of x. H is 3x, h prime is 3. This is fine. This is the answer. Maybe people would more commonly write it without dots like this. 3x squared, secant squared 3x. It's understood there's multiplications in here. Plus 2x tangent of 3x. Are there other ways to write the answer? Yeah, you could get these things in terms of sine and cosine. You could try getting a common denominator, which would be cos squared 3x, and add the two fractions. It's probably not worth the effort. This is good enough. For the purpose of using this derivative, can we factor anything out? You can factor an x out. Is that useful? Maybe. It's not clear because it's still pretty complicated looking. I guess one thing that's useful for is to see the derivative is 0 when x is 0, right? Because that'll be 0 when x is 0. That's one thing the factoring is good for. But any other spots where this derivative is 0 is based on where that's 0, and I don't think I want to solve for that where that's 0. And I'm the professor. I don't think I want to do that. It's probably not possible. It's complicated enough that it's probably not possible to solve for where this equals 0 exactly. So I think I'll stop right there. This is good enough for the gateway. In fact, that's good enough for the gateway too. But factoring it like this is a little bit more useful for homework problems when you need to use the derivative to help you make graphs. Let me show you, before we talk about reasons why the quotient rule and chain rule work, I'm going to show you something kind of neat. I think it's neat. That is related to something you should know for the gateway. And what I'm about to show you, we're going to do the similar things next week. Probably each day next week, we're going to do something similar to what I'm about to show you. I think this is really cool. What about inverse tangent and its derivative? I'm about to write something that's wrong. So after I write it, I'm going to scratch it out. Don't write this down because it's wrong. Okay. Some people might think inverse tangent of x is maybe it's inverse sine of x over inverse cosine of x. No, wrong. Pretend you never saw that. Bad, 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 bad. Well, what if that's not what inverse tangent is? What is it? It's the inverse function of the tangent function. We talked about this second week of class. The tangent function, that black graph, doesn't have an inverse, doesn't pass the horizontal line test. Every horizontal line goes through it infinitely many times. It's not 1-to-1, it's infinity to 1. Oh, but wait a minute, we always make a compromise. Why don't we just take one piece of the tangent function, like this one in the middle, and ignore everything else? The inverse tangent function is the inverse of that 1-to-1 function. I'm ignoring every other part of the graph. That little piece between negative pi over 2 and positive pi over 2 is 1-to-1. And I can use the reflection property to try to draw the graph of inverse tangent then. So here again is the tangent graph. Inputs between negative pi over 2 and positive pi over 2, not including the endpoints, because you got vertical asymptotes at the endpoints. So that's y equals tangent of x for x strictly between negative pi over 2 and positive pi over 2. What does its inverse function look like if I make the independent variable for inverse tangent x instead of y? I got to reflect it across the line y equals x. That's y equals x. And what will it look like when I do so? Where'd my green pen go? There it is. Okay. A little hard to do when you're looking at the graph like this. A little easier if you turn the graph like that. Reflect this part, you're going to get something looking like that. Reflect this part, you're going to get something look like that. It's still kind of tricky to do this. That's the graph of inverse tangent. And if the graph of tangent's got vertical asymptotes at negative pi over 2 and positive pi over 2, I guess that means this green graph has horizontal asymptotes at pi over 2 and negative pi over 2. Yes, that's true. That's y equals inverse tangent of x. This is actually a very useful function in lots of applications that don't necessarily involve right triangles. Why is it useful in applications that don't necessarily involve right triangles? It's perhaps the simplest function that's got two different horizontal asymptotes. And it's got kind of a pretty shape to it, kind of an elongated S, you could even imagine, representing a quantity that's growing from one value to another over time, say, like a population maybe. Although you wouldn't have negative populations, so you'd have to shift it upward. So you have positive populations, you'd have to translate it upward. It's sort of a prototypical application of a graph like this. Being such a nice graph, you might want to know its derivative. Is it inverse secant squared or something like that? No. The derivative of this is not a trig function at all. How can it be figured out? Through a fun trick. Tangent of inverse tangent of x, by definition of inverse functions, is x, right? When you compose a function and its inverse function at a value of x, you get x back. As long as x is in the domain, actually. But wait a minute, the domain of inverse tangent is actually all real numbers. This green graph is defined for all x values. This is true for all x. X doesn't have to be between, like, I don't know, -1 and 1, like with inverse sine and inverse cosine. It can be anything. You can plug in any number into inverse tangent in your calculator. The output's going to be between negative pi over 2 and positive pi over 2, thought of as an angle, and it's going to be in the first or fourth quadrant if you think of it as an angle, but not the input. The input can be anything. That's composition. I should be able to differentiate it with the chain rule, right? Composition. And I know the derivative of the outside function, secant squared. Take the derivative of both sides. Derivative of tangent is secant squared. I'm using the chain rule. Plug in the inside function. Multiply times the derivative of the inside function. Oh no, what do I do? That would be the derivative that I'm trying to find in the first place. Well, we don't know it, so just write it like this. And wait a minute, the right side's easy to differentiate. 1. And look at this equation. This quantity times this quantity equals 1. I can solve for the quantity that I want to know. Ah, algebra. Therefore, 3 dots means therefore d dx of inverse tangent of x is 1 over secant squared inverse tangent of x. Wait a minute, Dr. Kinney, didn't you just say the answer doesn't involve secant squared? Yes, I did. But wait a minute, it's there. Well, we can get rid of it. How? There's a few different ways to get rid of the secant squared and the inverse tangent and get what's not a trig function. This function looks like it's a trig function, but it's actually not when you simplify it. It only looks that way. Perhaps the easiest way to think about getting rid of it is to think about a right triangle. It's not the only way to get rid of it, and maybe it's not even the most rigorous way, but the way we're going to do it. Imagine, for the sake of solving for this, that this inverse tangent of x is one of the angles that's not the right angle, not the right angle. Like maybe it's this angle here. Pretend this angle theta is inverse tangent of x. Can I do such a pretending? Why not? Okay, I could pretend x is, I could pretend x is positive and pretend I've got inverse tangent of x, which could be thought of as an angle. You take sine, cosine, and tangent of angles. Inverse sine, inverse cosine, and inverse tangent of numbers could be thought of as angles. Now use SOHCAHTOA. TOA. Tangent of this angle is opposite over adjacent. This side over this side. But wait a minute, tangent of this angle is x. That's this equation. So opposite over adjacent has got to be x. So maybe this should be x and this should be 1. So that opposite over adjacent is x over 1, which is x. That's one possibility. Maybe also 2x over 2, 3x over 3, 4x over 4. Turns out to not matter. You might as well pick the simplest one. X over 1. The tangent of this angle is opposite over adjacent, which is x over 1, which is x. Because tangent and inverse tangent satisfy this property. And what am I trying to do here? I'm trying to take the secant squared of that angle, which is the same as the cos, or 1 over the secant squared, which is the same as cos squared of the angle. And cosine is adjacent over hypotenuse. So CAH, C-A-H. Adjacent over hypotenuse. Oh, I got to figure out the hypotenuse. Use the Pythagorean theorem. It's a right triangle. If you do so, you'll get square root of 1 plus x squared. Think about that. The Pythagorean theorem says the hypotenuse squared equals this squared plus that squared. So the hypotenuse itself has got to be the square root of the sum of the squares of these two things. Cosine of this angle is adjacent over hypotenuse, 1 over square root of 1 plus x squared. I'm taking the cosine of this angle and I'm squaring it. So I get this, which simplifies to this, and that's not a trig function. So yes, it looks like it's a trig function. You can represent it in terms of trig functions, but in the end, it's really not. You can simplify it to something that doesn't involve any trigonometry at all. That is the derivative of inverse tangent of x. It's also the derivative of arctangent of x. Why? Because arctangent of x and inverse tangent of the x are different notations for the exact same function. I believe arctangent's actually the older notation, historically speaking, and inverse tangent's the newer notation. But both of these symbols represent the exact same function, therefore they have the exact same derivative. This fact right here, written either with inverse tangent or arctangent, is something you should memorize for the gateway. When will it show up on homework? Not until section 3.5 next week. But I'm showing this to you as kind of a cool application of the chain rule, which is what we're focused on right now and for the rest of our time today for the most part, except for one other thing. It's an application of the chain rule. I use the chain rule here. Kind of a neat application of the chain rule. Again, do you see how I use the chain rule? That's a composition. Tangent is the outside function. Inverse tangent is the inside function. I took the derivative of the outside. The derivative of tangent is secant squared. Plugged in the inside function, then multiplied times the derivative of the inside function, which I did not know ahead of time, but I can still write it symbolically like this and then solve this equation for that unknown derivative. And it turns out you can simplify it nicely. What does the graph of this function look like? Graph 1 over 1 plus x squared, it turns out to look about like this. Kind of like a bell-shaped curve in statistics. It's not the true bell-shaped curve from statistics, but it looks like one. That's y equals 1 over 1 plus x squared. And it is giving you the slopes of the green graph. Close to 0, but they're always positive. Close to 0 over here. Maximize when x is 0, just like this function is highest when x is 0. Then they go down close to 0 again. But they're always positive, so this purple graph is always positive. To tell you the truth, this fact, though we emphasize it here in Calc 1, that these are equal, and you're tested on the gateway, to tell you the truth, the most important application of this fact is in Calculus 2 for doing integrals. Antiderivatives. The derivative of this is that, therefore the antiderivative of this is that. That's a big thing in Calculus 2. This gets used all the time in Calculus 2. Right? That's the more important application.